So before Param teaches you all practical things, I'll tell you about good old times. Because for me, good old times was the times when I was young, and life was beautiful and things were wonderful. So when I was young...
And all programmers were above average.
All the programmers were above average, yes. So when I was young, and the time of my youth is roughly the end of 60s, early 70s, several things happened. One thing happened was that people invented this fundamental separation between two things. Again, in words of Niklaus Wirth, people invented that there are algorithms and data structures. Yes? And let us think about what they meant. It was at first a fairly theoretical separation because most programming languages people programmed in had difficulty either implementing algorithms or data structures. What I mean by that is that mean we implemented last time was unimplementable. But the same thing was true about data structures. Sort of data structures which were commonly accessible, for example, if we take Algol 60, the only data structures available to a programmer were arrays. And you could at least get variable size arrays. You say, what's the big deal? Well, observe that when C appeared, even that disappeared. Sort of the variable size arrays became inaccessible. So we will get to that in a second. To do other kind of data structures, you had to do something dramatic, like switch to Lisp. This is why people were running around and saying Lisp were wonderful, because it allowed you a construction of at least a linked list, which by itself appeared to be a great accomplishment. Of course, it didn't even do that correctly. Let us observe the remarkable thing about Lisp, which makes singly linked list its fundamental data structure, yes? But what it does, it makes a fundamental confusion between linked list and position in a linked list. Yes? If you have a data structure called linked list, you could have a pointer, or what we now would call an iterator, into this linked list. Lisp does not allow you to do that. In order to traverse linked list, you have to get ever so small linked list. There is no separation between data structure and an iterator, which forced people to invent garbage collection, because you couldn't possibly distinguish ownership from position. We shall see. This is I'm setting a stage for many things which we will be doing, right? They're distinct notions, but they were not realized. Of course, then people also observed that there is sometimes a necessity to group things together. Again, let's go back to Algol 60. There were no structs. You say, how did people live without structs? They lived quite well because what they learned to do is to construct parallel arrays. Right? For example, let us assume that they needed what now you would do as a vector of pairs. Most of you probably know what a vector of pairs is. What would they do? They would have two arrays. One array pointing to the first, and the second array pointing to the second. So that was the standard solution. Structs did not exist. The interesting fact is, it's the precisely appearance of structs which killed arrays. You see, in algol 60, arrays could contain either real numbers or integers or booleans. There was nothing else you could put in there. The moment people invented structs, the question appeared, could arrays contain structs? What do you think? Should they? Yeah, they should, obviously, yes. But then the second question comes. Should structs contain arrays? Should they? Why not? Seems to be a useful thing. Well, but if structs could contain arrays and arrays could contain structs, then if you have variable size arrays, you're doomed. Do you see what I mean? Because if you have an array containing struct and the struct contains variable size array, it is a variable size struct, and random access to the array disappears. So it appears to be an unsolvable problem. It is actually perfectly solvable, as we shall see. But the problem is at the time it caused the fact that the only array type, for example, in C, is a constant size array. That's the only thing you could put in a struct. Of course, C goes beyond even that. C doesn't make arrays real types. Why? What do I mean by that? What's the issue? Why they're not full citizens of the type system? What couldn't you do with arrays? You cannot find size. Why don't you find size? Because the way arrays are handled is that if you pass them to a function, you pass a pointer, the size is gone. Right? That is, if you cannot pass arrays by value, everything else in C you pass by value. If you pass a struct, or at least after, it's more complicated than that. Original C, when it had structs, you couldn't pass them to a function. You could only pass a pointer to a struct. Then they figured out how to pass a struct. By the way, how did they pass a struct? What was the semantics? It's a tricky question.
They just put all the data on a stack, right?
What do you mean by that? Shallow copy. They would copy the bits. The rule in C was that when you pass a struct, you copy the bits. It will bite us very soon. Because, of course, C++ originally inherited this rule, that if you pass a struct, if you construct it, if you assign it, you just copy the bits. Why is it bad? It's very bad for things like what? For arrays, it actually works. Dennis was careful. He figured out it works for arrays. If struct contains an array, you copy the bits, array is copied. Heap allocated objects. That is, if you have constructors, everything breaks. As we will discover later on, C had to come up with a new rule that when you copy something, instead of doing a bit copy, you have to do component by component copy. Do you see the difference? If I have a structure containing first and second, instead of just copying the bit patterns, I have to use copy on first and copy on second, doing this recursive descent. Right? And because if first contains first and second. 2, you have to, so that becomes, in some sense, deep copy. Or correct, we'll see. It's very,
depending on whatever the type decides to do. But
it's whatever the type decides to do.
this also clarifies issues with alignment. If there are parts of your struct that need to be aligned, this definition handles that.
The old definition handles it too,
in
because
more
it's a bit
complicated way.
copy. The interesting thing, of course, happens with padding, because the original thing assured that the padding would be copied. The new definition, of course, tells you nothing about the padding. Because if there is a padding, you don't have to do anything with it. Right? But again, sort of, I want to tell you a little bit about, but the problem which was still outstanding was how do you incorporate data structures into the language. And interestingly enough, that's what we are going to try to learn. How do you build data structures? What are the issues? And I claim that it took us a long while since the 60s till we learned to implement in a relatively consistent way things like variable size arrays and linked lists and trees of all kinds with a consistent semantics. So, and now I let Parham continue.
Okay, so we'll start with a very basic data structure, pair. Right? So as we've talked about already, programming consists of modeling a real-world problem using bits. Right? So if you're designing data structure, what should we do first? We need to figure out what are the bits that we're talking about. Right? So what is a pair? A pair is two things together somehow. Right? What do we mean? How do we want to store it? So one way of storing it would be you just say, okay, we have some block of memory, and first we have our first thing, and then we have our second thing. Right? So this would be one way of having a pair, and that's what a pair is in C++. It is
No, it isn't.
just this. What is it then if it's not this?
The picture is not correct.
Well, with potential padding, you mean, or what else?
With potential padding, I mean. And with that's an important thing.
Yes.
Every type in just we have to talk a little bit about sort of C model of how types are stored. Every type has two fundamental attributes. One attribute which is actually well defined in the language is called what? Size of. Right? It's a number which tells you how many bytes a type occupies. Then there is another attribute, which sort of harder to find, but it exists. It's absolutely it's alignment of. Let us use the same.
Yes.
So alignment of tells you where the language would put the type. Why does alignment is important? Why is alignment important? Explain. Why couldn't we just put stuff any place we like? Some processes do not even support it. That is correct. Once upon a time, this process is becoming more and more obsolete with every day, but once upon a time, you couldn't rely on the fact that if you have a 4-byte sequence starting with an arbitrary boundary, and you attempt to load word or whatever, load 4-byte quantity from that, this will work. A bus error was a common situation. Many of us, I'm sure, Neil and Paul, older people, sort of encountered it. You attempt to do it, you forget about alignment, and the computer breaks, the processor melts, whatever, some terrible things happen. So alignment was this important attribute. We shall see even in this sort of course when it becomes. Of course, now things are changing, you could often use very efficiently for performance things called unaligned reads. So,
So I mean, as Greg said, even on processors which did support loading an arbitrary type from an arbitrary location, performance was often not good because you had to load it and shift it and all of that. And it turns out that at least modern x86 processors do them practically as fast as aligned reads.
And you could do wonderful things. It's a very important technique which you need to be aware of. So we'll get to that. But again, alignment is very important thing to remember. So when we have a pair, this could be, for example, a thing which aligns, the whole thing will align on a word, 4 bytes. Then the first thing would be a thing which aligns on half word. And the second thing, for example, this is short, assuming short is 2 bytes. And this is going to be an int, assuming that int is 4 bytes. There will be a 2-byte gap in between, padding. Yes? So this, I just wanted to sort of never assume that two things are allocated right one after another. Never assume that the address of the second thing is going to be address of the
First
struct plus size of the first field.
So size of the pair includes the file.
Yes. Yes. The size of the pair is not less than the sum of the sizes. Let us be precise. But it's not equal. The mistake which we sort of make is that we assume intuitively, sort of, so obviously we have a struct, we just add the sizes. No, it doesn't quite work.
So the order of the elements will change, not in a the order
There were people who tried to change it, but that will break just about every hardware device and every single device driver in the world. Because you see hardware devices, when you specify that it's this that follows this, it better be true. Because hardware does not do reordering. Right?
I mean,
So yes,
does not
it is
say
guaranteed.
that the layout is up to the compiler. The language says you define your alignments and your sizes, and then it must be as follows. Right? So if you're writing a device driver, you can rely on it. You can say, okay, if I have a memory mapped device that has registers in the following locations, I can create a struct that I can use to write to that thing.
And all the clever people scream about it, but they are wrong. It's actually very good that we could precisely describe memory layout for hardware, for network protocols, for things like that. We really do not want sort of arbitrary, I mean, that will break, nothing will work. Right? So, again, sometimes there's this pseudo-mathematicians who say, well, we want freedom. No, you want precision.
Just to go back to alignment, it's a relatively recent phenomenon that unaligned reads are fast.
Yes.
Because 10 or 15 years ago, they definitely weren't.
No, even I would suspect less than 10 or 15 years ago they weren't. It's only with the very recent processors that they seem to be very fast.
But
And I'm not sure if that is true on mobile platforms, for example. I mean, we know that it's true for latest x86.
well, for Intel done fabulous job on unaligned read. We'll study that. But the important thing to remember, the alignment still exists. You have to think about it, that things are aligned. Like when you write an int, this int will be aligned. If you want to deal with unaligned integer quantities, you need to do tricks. If you write int a, this int will be aligned on an integer boundary. If you write double, it will be aligned on 8-byte boundary. Right? Again, you could do tricks. Don't do tricks with double, but within trick could be quite useful, as we shall see.
Yes.
Sorry.
Okay, so let's just try to define this thing that we've sketched out here. We have two types next to each other with potential padding in the middle, right? So how would you do that in C++? Should I write, or does one of you want to?
Let them write, let them write. Jerry is anxious.
Does someone want to take a shot at it?
You cannot say T1, T2? No, you cannot say T1, T2.
Okay, so you were defining a pair.
Okay, right now, let's ask them. Why does he say struct and not class? And why do we like it?
Define functions just to get at our elements.
Which would be silly against. Many of you, and I see it in our code, often do the thing because some great man wrote some great book, which tells you that you have to write
Get first,
class,
set first,
pair,
get second,
and
set
have
second.
provide getters and setters. Do not do it. There is a perfectly good way for a setter. It's called assignment. Just let people use the normal thing. And there is a perfectly good thing for a getter, dot operator. I mean, it just gives you the stuff. You say, well, but what if I want to change the implementation of a pair? Well, then you have to have your head examined. I mean, why would anybody ever want to, sort of say it's more abstract? No, it's not more abstract. This is a perfectly good abstraction.
I mean, if there's an invariant you want to maintain, let's say you're allocating some memory, you want to keep track of some state regarding it, it makes some sense to make that be private and have some access methods. But in this case, what did we want? Our goal was we have these two types that are sort of one thing, and we want to be able to read and write both of them. There are no invariants here. We want to be able to read and write both of them. There is nothing private about this. This gives you nothing.
So why would you want to set a breakpoint?
Because I want to see who corrects the structure and writes zero.
Well, most debuggers will let you see how, this probably you will put it someplace in memory.
Yeah, most debuggers have memory breakpoints.
Yes. So, again, since you have been taught by great authorities to define getters and setters, I want to strongly urge you not to. Yes? That it's, yes? Yes. Yes. I'm talking about, right now, a very simple thing. I'm talking, well, okay, let me, okay.
No,
Time for a diatribe. Thank you.
So I didn't understand the question. Can you repeat the question?
That it depends, this is his usual thing. Here. Sort of, in Java, it means something completely different. Of course. But let us backtrack from before we have any language. Sort of, I actually claim that the fundamental thing in programming are things called bits. It is, there are these people, again, who have been trying to explain to you that the task of a language designer, of a programmer, is to hide bits. I think they are misguided and, there is another word, stupid. Because the great discovery, which sort of goes back ages, is the fact that you could use bits to represent everything. By the way, who discovered bits? Okay. Obviously you know, but
And
okay.
I think we even,
Leibniz.
yes. So I mean, clearly nobody's paying attention because we talked about Leibniz once in the bits lecture.
Yes, but let us just explain that. There was a great German philosopher and mathematician, Gottlieb Friedrich Leibniz, who stood, he is this wonderful person in many respects, so you need to know about him. And he viewed himself as a Pythagorean. What did he mean by that? Why did he call himself a Pythagorean? Some of you attended, at least were physically present during the journey course. So what was the fundamental discovery of Pythagoras? What did he say? What was, come on, Jack, that's part of the story. You should remember that. It's not mathematics. Yeah, it's part of the ship battles, yes. So, what was the fundamental great breakthrough of Pythagoras and Pythagorean school? They came up with the fundamental, astonishing idea that everything can be described with numbers, right? Because prior to that, it was something accountants did. It was for Dana and her friends. And the scientists, they contemplated the skies. And here comes Pythagoras, and he takes numbers away from Dana. And he says that these numbers, this stuff accountants use, could describe everything. You say, it's self-evident. Well, apparently it wasn't, since, prior to that, nobody thought of that. Yes? So this is why Leibniz called himself a Pythagorean. He also believed that there is this possibility to use a universal language to describe the world, to describe science, yes? And then he realized something. Leibniz is one of the people who, there are a bunch of them, who thought about creating this formal language which could describe reality mathematically based. And as part of that, he realized that you could base this language on zeros and ones, on bits. And guess what? He was right. Every day you paid big bucks because of Leibniz. What you do is with bits. And I want to stand up and loudly say, bits are wonderful. Hiding bits, hiding this great universal language is a stupid idea. Why should we be ashamed of them? People say, oh, let us replace them with lambdas. No, let us not replace bits. Bits are fundamental. That was Leibniz's observation. And then at the beginning of our field comes Alan Turing. And by the way, what does he invent? He builds this thing you might have heard called Turing machine. And it deals with bits, zeros and ones. He realizes that you could build a machine. These are good things. Let us not be ashamed of them. So there is this marvelous thing, not provable, of course, that you could represent everything as a sequence of zeros and ones. Yes? This binary value. And our view of the thing, at least Paul and my view of the thing, that's what values are. Values are sequences of zeros and ones together with their interpretation. Let me just, for a second, not talk about that. But zeros and ones are very good. So when we're talking about this thing, I'm not talking about C++, I'm not talking about Java. I'm talking about value. Some languages allow me to get to values easier. Some languages, such as, say, Python, makes it utterly impossible for me. Unless I do, yes, you could have something where bits are distinguishable. But the moment I start writing integers, bits disappear. The moment I write 5, who knows what this 5 becomes? Yes? Which is very sad. I do not enjoy it. The fact that they replace a well-defined 101, that's 5 for those with some unspecified thing. I think it's terrible. I prefer clarity of this thing. So when we talk about pair, what we're trying to get by passing the C++ or Java or Python, we're trying to get there is something here followed by something there as close as possible. Again, machine might not allow us to put them side by side because there are limitations on sort of read instruction, or at least potential limitations. He says there might be a limitation. But this is what we're trying to get. I mean, in some sense, this is if you want to describe my view of programming, I'm a bit programmer. You know, I'm not a C++ programmer. I'm 0 and 1 programmer, right? I'm a Pythagorean. You know, I like Leibniz and I like Turing. But so I don't know if it answers any of your things. So what we're trying to get is sort of the abstract view of the most primitive pair. As we will see, there are difficulties there. And we'll try to do it abstractly using C++ only because, and again, he's sort of, why do I use C++? Because it made me rich and famous. No, guys, for sure not rich. And famous, whatever attributes of fame you might think exist, they're not desirable. It basically means that random people could send you email messages saying something you don't want to hear. And they do. Sometimes they compliment you, sometimes you say, oh, you're a fool, you don't understand, you should read a book on Python. So why do I use C++? Thank you. I use C++ because it's the only language which allows me to get to the bits. It's the most Leibniz sympathetic language in existence, right? When I write an integer, or at least when I write an unsigned integer, I could be almost certain what kind of bits. Why I'm almost certain? Anybody knows? It's worse than that. Endianness. So, I mean, we shall see. Even C++ does not get me as close to bits as I would like, but it's clearly closer than these languages, you know.
And even from a very practical point of view, I mean, what is programming? There's this dumb piece of hardware which is useless unless you can make it do something, right? You have to know, ultimately it's about what is in that thing. There are bits. You have to know what's going on with the bits. And you may use a higher level tool to do that, but we've seen in the first few lectures that how the bits are laid out can have fairly dramatic effects on whether your thing works. So you have to ultimately be able to think about the bits, and you have to say, okay, I want my data structure to be this way. How do I achieve that with whatever tool I have? And if the tool hides them a little bit, I have to, you know, trick it into doing what I want, but I still need to know about how do I want these things to be laid out. Do I want them to be like this? Do I want them to be like, you know, 2 pointers to some other piece of memory? Do I want something else? You need to know what this looks like to be able to do what you want. Otherwise, your thing is not going to work very well. So you need to know what's going on at the bit level.
And part of the problem, very, very correct. I mean, we need to get to the computers. And computers gradually got us to almost bit level precision. We're still not there. Okay? remember that when I was starting or Paul was starting, if you wrote in a high-level language, you had absolutely no idea how long your int was. Most likely it was 36. By the way, observe not divisible by 8. It was very common. It could be 60 on some of the machines Paul was starting. Control data liked that because you could divide 60 by 15, which is obviously a very natural size of things. But they did deal with 15-bit units. Yes? And Seymour Cray, the greatest computer architect, thought that 60, which is 4 times 15, is a very natural thing. By the way, or 6 times 10, or 10 times 6. Well, characters were 6 bits long. So you could put, and you say, well, you couldn't put too many characters. Well, you don't need too many characters. Who needs lowercase? Seconds? No. It had nothing to do with the seconds. Interesting enough, it had to do with the fact that 60 was long enough for floating point numbers. That was before 64-bit IEEE standards. So you could have a mantissa long enough. So physicists were happy. It allowed you to divide it into 4 15-bit units, and obviously 15-bit instructions could be put 4 at the time in a 60-bit word. And then you could pack 10 characters. And nobody actually, at that time, nobody even dreamt of 8-bit characters because it would be oh so very wasteful. Never mind Unicode. So that was the time. So you couldn't then, again, we're going back, we talked about it. Sort of IBM successfully imposed bytes upon the world. We should thank IBM for bytes, right? Sort of they made this universal architecture system 360, which was based on 8-bit bytes and byte addressability. Every byte was addressable. The order of bytes in an int, however, still remains unspecified. IBM was always in favor of big endian. Intel was always in favor of little endian. We shall see what it means when we get to it. So it's not specified, and the languages are not very good dealing with that, sadly enough.
There were some other variants that were jokingly referred to as middle endian, but let's not go there.
Yes. But, and again, sort of, we are settled now in terms of signed. Two complement representation of integers could be safely assumed. Paul and I couldn't assume that. You know, there was sign, we talked all about it. So again, sort of representation of bits is still a major problem. If you live another 20, 30 years, maybe we'll get to the point where you could precisely specify like bit layout of everything and it will all work nicely. But it's still a long ways off. So apparently we're not very good at doing even simplest things such as integers.
And the fact about knowing what's going on in the machine really is important, I mean, at all levels of the computer, right? If you're working with a database, yes, SQL is a nice declarative language. If you want to write good SQL queries, you'd better have an understanding of what is the database going to do when I do this. What indexes do I have? What tables do I have? What access methods do I have? You cannot write a good query without understanding that. And yes, the language is declarative, but in your mind, you're thinking, okay, if I type this in, this will happen. That is how you write good database code. I mean, if you're writing even, let's say, Prolog, right? Yes, fine.
Don't say that. No, in case of Prolog, you probably don't want to think.
Yeah. No, even in Prolog, you write Prolog code, you have to be very aware of this is what the execution order is going to be. Otherwise, you couldn't, I mean, you had to think like that.
Don't write Prolog. That's my advice. I'm not, you know. I'm joking.
Yes. Okay, so we
Paul
have a
has
pair.
a friend who is a great Prolog programmer and very charming and wonderful person. You know, I like him. So there are good Prolog people. I just want to. It's like, you know, old anti-Semitic arguments. I'm not an anti-Semite. I have a Jewish friend. So, you know, but no. Prolog is strange.
The police is coming to catch us for the pair. But anyway, so we have the pair. It has
Let's
two
go
members.
eat, and
Is
then
that
we will do
sufficient?
pair.
That is the question you should ponder while you eat. I mean, are we done? We described the memory layout. I think that does it. You know, but we can talk about if there's anything more after food.
Just before, let us tell you just a little thing. Some of you might know, but I'm the guy who inflicted pair onto the world. Before that, you were supposed to write your own things and blah, blah, blah. So, and when I implemented pair, it was like 15 lines. Not 4, not 5, 15. So there's some more stuff. How long is pair now? In the
A few hundred.
So we will not get to that level. We'll stop at about 15. But everything grows. Whatever you do expands.